Welcome to How Science Happens, a podcast by Wally Paxton, DJ So, and Doug Tree, professors at Brigham Young University. In the podcast, we bring you stories of cutting-edge science as told by world-class scientists and engineers from around the world who are on the front lines doing the work. We explore the highs and lows of discovery and what makes science such an exhilarating and frustrating process for those who do it. And because we're nerds, maybe we'll even learn a little science along the way. Hi, everybody. Welcome to another episode of How Science Happens. My name is Doug Tree, and my co-hosts today that are joining me are Wally Paxton.
Hey, everybody.
And DJ So.
Hey, everyone.
So we're super excited to have Todd Squires, who's a professor in chemical engineering at the University of California, Santa Barbara, with us on the podcast today. Welcome, Todd.
Thank you. Happy to be here.
Super. We're super excited to have you. So Todd comes to us, like I said, from UCSB. He has a bachelor's in physics and a BA also in Russian, which I found interesting, from UCLA, if I'm not mistaken. He has a certificate of advanced studies, if I got the right acronym there, from the Department of Applied Math and Theoretical Physics at Cambridge. And then he did a PhD in physics at Harvard and was a Lee A. Dubridge Prize postdoctoral fellow at Caltech. And he's highly awarded, very successful researcher and academic. Most recently, I noticed that he won an early career award from GSoft, which is through the American Physical Society. And he's a—
Congratulations.
Well, thank you.
And he's a fellow, APS fellow with the Division of Fluid Dynamics. So we're super excited to have you today.
Well, thank you. And I will correct you, actually. It's not the Department of Applied Math and Theoretical Physics, because it's in England.
Oh,
and so
maths.
It's the Department of Applied Maths.
Yeah, thank you. Yeah, you can't forget the S on that.
Well, there's more than one. It's not mathematic.
That's
mathematics.
right. That's right. So we usually start out with hearing a little bit about your background and how you got interested. So you come into a chemical engineering department, but your background's in physics. So I'm interested to hear a little bit about that, and you know, how did you get interested in physics in the first place? Was this something that you were sort of always excited about? Were you staring at the stars as a kid, or what was it about physics that drew you in?
So it was largely random, Doug, just to let you know.
Yeah.
So when I was I always kind of liked science as a kid. I was actually a very shy kid, which is, I don't know. I mean, I'm kind of surprised at it when I look back, but I was very nervous and very shy. And I think so I liked, we had one of the early IBM personal computers. And so I would learn to program in BASIC. And I think there's the part of me that enjoyed, being able to control, like, oh, I can make this thing do what I want it to do. And, and that's a lot easier than dealing with, other junior high school kids.
Yep.
But so I liked science. And it was my senior year of high school. I had never taken physics, didn't know what it was. And we had to take a science class, and it was physics or physiology. And I honestly didn't know the difference between them.
They both start with a phys. So.
Yeah, that's right. And so I just picked one at random, and, and then something about it really appealed to me. And, so I decided, I'll do that in college, so it was not terribly well thought out, and I think there's a lot of things like that with me, where I'm not necessarily setting out to do something that I've planned meticulously, but I just, you find what's interesting in what you are doing. So.
Awesome. So was that similar with Russian then, or was that something like, had you had previous experience, or did you just go, that seems like an awesome language, I want to learn that?
Yeah. I mean, so I had a good friend in high school who was a real, poet, basically, and was very, very literary. And so he and I kind of developed a bit of a, militant intellectual kind of thing in 11th grade, and I read a lot, but it was basically because he liked to and we talk about it, and we sort of joked about learning Russian. This is Cold War era, by
Yeah.
the way. So I'm old
Yeah.
enough, and we thought, oh, it'd be funny to learn Russian. We could like make people nervous, and
Talk
I
in the
got to-
grocery store.
yeah, and I got to UCLA.
Uh-huh.
I'd taken Spanish in high school, and I didn't, you have to take a year of language in college, and I didn't pass out of Spanish. I think I
Okay.
passed out of 1/4, and I didn't feel confident enough to move into the second quarter right away. And so I thought, oh, you know what, I'll do Russian because I like the literature, and and then I really loved it. Actually, I almost didn't. Physics was kind of easy. The math, the chemistry, all of that stuff was basically easy for me. But it was taught in these like 300-person classrooms,
Yeah.
and nobody was particularly interested in being there. Most of the students weren't. Most of the faculty weren't. And then I go to Russian, and it's like 12 people. Everybody knows everybody, and so then it was the rebel in me. I was kind of like, oh yeah, I'm going to be a lit guy, like I'll be a lit crit, and so I almost didn't even finish the physics degree. I thought, oh, I'll do this.
So do you still speak Russian?
Yeah, no,
Okay.
it's so I did a semester abroad in Moscow when I was in so it was 94. It was so it took me 5 years to do this double degree, not surprisingly. And that really cemented it. Like I think once you become conversational in a language, then I mean, my vocabulary is not what it used to be, but I can talk my way around anything I need to. So yeah. And I like languages. I think, a lot of times mathematical minds kind of enjoy languages. So
Yeah, I resonate with that. Oh, sorry, Wally, go ahead.
I think at BYU, doesn't math qualify as a foreign language credit? Or at some point it did.
You're kidding. Is that true?
That's true.
Yes, you did.
They count math as a language credit.
Wow.
Anyway.
Well, you have to learn the Greek alphabet, I guess. So.
Yeah, there you go.
Yeah, we end up at BYU having a lot of students with foreign languages, though, because of LDS missions.
Yeah,
so
right.
A lot of students do missions. So like, for instance, DJ did a mission. DJ's from Korea and served a mission in Oakland and learned English.
Okay.
And I did a mission in France and learned French.
Okay.
And Wally, I can't remember, did you serve a mission?
I learned English when I went to California. My English is much better now too.
You can pass for Californian.
I think so.
All right.
He knows how to wear shorts just right.
That's right.
So tell us a little bit. So you were telling us a little bit in discussion beforehand how you were in Russia and thinking about, in your study abroad, thinking about grad school, and that led you to Cambridge. That was a really interesting story. Do you want to tell us a little bit about how that came about?
Yeah, well, I mean, so I had, so at some point in undergrad, I decided to kind of accept something about myself, which is that I'm actually really good at science, and that, that as much as I thought of myself as this kind of hip, lit theory guy, like this is something I'm really good at and I enjoy. And so I decided to finish that up. And so I wanted to go to grad school. But I didn't want to take the GRE when I was in Moscow because I thought, oh, I should be out, enjoying this experience of being
you had this limited time to be there, right?
Yeah. And, so I asked my research advisors and undergraduate what I'm like, oh, at first I said, oh, can I just spend a year working in your lab, when I'm done, and then I'll apply for grad school from there. He was an English guy, and he said, oh, the one thing that I wish I had done after I had been, after my undergraduate was this Part 3 program at Cambridge, which is sort of the, the Cambridge will say, oh, it's the oldest and most difficult mathematics exam in the world, right? And Isaac Newton took it, and he said, but it's basically like a year of it's a taught master's course, but it's really interesting, high level specialized, courses, and it could be particle physics, could be applied math, as I did asymptotic methods while I was there, a bunch of fluid mechanics, because the strongest kind of fluids group in the world. And so I thought, oh yeah, it sounds really great. That sounds great. Let me, he says, oh, you can probably get a scholarship to do that. And so I kind of thought, oh yeah, I'll do that. And so I was like applying for these things. And then the irony is that I had to take the GRE anyway. And so fortunately, I don't know if you guys require the GRE, but like at that time, you just had to not embarrass yourself, because the GRE really, it says nothing about your your abilities as a as a scientist or as a potential peer.
Yeah, a lot of
PhD.
conversations about that going on.
Yeah, because anybody who's mathematically minded is basically going to top out the math part, right? Because it's like SAT level math, and and so I didn't embarrass myself. It was okay. I mean, I didn't do great, but because I didn't study for it at all. I didn't prepare. I had never even looked at a practice one, because I was out being a a student in Moscow, and loving the wild west that Moscow was in 1994. So eventually I wound up getting a Churchill scholarship, and spent the year there. It was phenomenal. Learned a lot. I took high level, I took a string theory class, I took quantum field theory, all of these things, because I kind of thought that that's what I would do. But then I also took fluids classes, and really found that I enjoyed those, and I kind of enjoyed being able to think deeply about the stuff that was all around us all the time, and for me, there was a real beauty to that. And I just found it kind of more and more, it drew me more and more over time, rather than I can sound really, really smart by talking about, 16-dimensional space. I mean, I'm sure that would have been interesting too, but
what sort of struck your curiosity or pulled you in was that element of, I'm doing this high level, difficult mathematics here, but then I can turn around and see an example of it, in my life or in daily life.
Yeah. And I think I enjoy, I enjoy interacting with people. I've always been a really curious person, and so I found that kind of set me down this path of really just being able to look at the world around me, the peanut butter that I spread on my bread, right? I mean, and that kind of gets us into soft matter, right? But like, you look at all these things and you say, wow, that's really wild. What's going on there? Or, if you're in the shower, you can kind of just see all of these things you can kind of see, and it's, it's sort of inspiring. I did Arabic in graduate school also. And I remember I at some point we had to write a term paper. I think it was in the third year. And so I wrote about the physics of sand dunes and sand ripples, and how they, because I was kind of interested in that at the time. And so I have this like 10-page, handwritten Arabic thing with diagrams and, and I remember, everybody else was, people who were in like, Middle Eastern studies or politics or something like that. And I remember the professor was sort of like, I will never look at those the same. And he says, to him, he was like, well, it seems like it, you've taken a little bit of the mystery and the magic out of it. I was like, well, no, it's the opposite. It's like, if you don't ask why that happens, then, then you're not thinking about it. You're not actually processing it, and just how incredible it is. It's kind of fun to understand that. So anyway, all of these sorts of things that,
That's awesome. Yeah, I love that. I hadn't realized that you'd done Arabic. I think that's really impressive too.
It doesn't show up in my CV, but it's a phenomenal. It's a beautiful, beautiful language, and especially for a scientist, I think, because there's this very elaborate structure to it that the more you study, the more you start to understand. And I sort of feel like it's kind of like what we do as scientists. You see the natural world around you, and at first everything seems random, and then you start to see patterns, and then and then like the more you go, the more you realize that this is related to that. And, and then at some point you're realizing that all of these words that you learned as a kid in English, oh, it's actually that Arabic word, or,
yes,
and anyway, so I don't know. So I don't know. I really enjoyed that. That's harder to keep up because the language that you learn is you learn a formal, the language that's taught is called Modern Standard Arabic, and it's a formal one that like speeches are given in,
okay,
but nobody speaks that
but
way.
right.
So,
Yeah.
so
it's hard to have the practice of speaking versus the practice of like, keeping up that formal.
Yeah, reading the newspaper, kind of going to a university lecture, that kind of thing. But like, you go to the market and you ask for bread, and it's like, you sound like Shakespeare, right? And they just kind of laugh at you and like, oh yeah, how nice of you to try,
You're like, I'm trying. It's that's something I've learned when learning a language. There's a level of humility, right?
Oh,
because an 8-year-old can run circles around you, right? And so it can be hard sometimes to want to just try. You can be embarrassed really easily, right?
Yeah.
So that's
and so here actually, so I'll put in a plug for the budding scientists around it, even the students too, because what you just said reminded me of something. Like there are times in Moscow where, you can just keep learning a language. And you can, and you get to the point I did where you can kind of say anything, right? But I'm still not going to say it the way that a native Russian would say it, right? And so there's these subtleties that you'll miss, or things that you mispronounce. And I remember there are times where I'd be out and I could tell that somebody was looking at me like I was stupid, right? And there's times where I have this frustration. I'm like, look, I'm really smart. If you let me speak in my own language, I can tell you all of this. And and at some point it occurred to me just, how much we hit the jackpot. Well, DJ didn't, right? But we're born in the country, where the language we learned growing up is the language of international science right now, right? And we didn't have to do anything to earn that, right? It's just given to us. And and so international scientists and professors, right, they have that extra barrier to overcome, right? And so I'll tell my students this sometime, like, look, just give people some benefit of the doubt. And especially, if like, don't make people earn your respect, and
So I sometimes talk to my students, freshman chemistry, and they're coming from all kinds of different disciplines. And I talk to them about chemistry being a foreign language because you have to learn all of these new terms and everything. But I'm going to think about that differently, because learning science in English from a foreign language can be even more difficult. And there's a lot of things that we take for granted, that all of those words that we are learning, they have some root in English or something close that makes it easier for students to grasp that, because English is their native language.
So while taking classes with in a college, we had a translated version of the textbook, like fluid mechanics textbook. And there are some words that can be translated. That's the reason why we have to learn English language. Of course, all those small words are in Korean, but the big word like perturbation, something like that, we have no way to interpret perturbation to the right Korean word. So it is true that if you know English, you have easy access to science.
Yeah.
And that's the language that we write all our papers in. And lucky us.
We should. If you have that, if that's your case, you should feel grateful and gracious to others, right? Who are So I want to sort of push us a little into starting to think about some of the technical things. So you did your PhD at Harvard and a postdoc at Caltech, and you got a lot into fluid mechanics, right? And into microfluidics, which is a lot your area, right? And so maybe, do you want to just give us a little, maybe a couple minute overview of just some of the problems you've worked on, and maybe then we'll use that to segue into kind of the current interest you have that we're going to talk about this paper on membrane models.
Yeah, before that, I have one quick dumb question.
Yeah,
Did
please.
Harvard ask you to take GRE again?
No, I think I don't think
didn't.
I
Oh,
took
that's
any
good.
extra anything.
Okay.
I don't know, I might have. I don't think I took the physics GRE in Moscow. I think I just took the general, and I know I had to take the physics one, which I also just did okay on.
Okay.
So,
Yeah.
you know, but so yeah, I did. So as a PhD student, I had two advisors, you know, and that's so Howard Stone and Michael Brenner, and you know, I can still see a lot of each of them in me, you know, in the way that I think and the way that I talk. And you know, so your advisor just plays an enormous role in your evolution, I think, as a scientist. And I did various projects kind of with each of them. And they involved, you know, they all involved complex fluids that weren't that complex. You know, it was like, you know, small colloidal spheres in viscous fluid. And there was a problem at the time where there were some experiments that suggested that, you know, similarly charged colloids, you know, I mean, every theory on the planet says that similarly charged colloids will repel each other, right? And but then there are some experiments that said, oh, if they're near a wall or if they're confined, then they can adopt an attractive interaction. And you know, this was very appealing to a lot of people. You know, because it's a real basic thing that you wouldn't expect to happen. You know, and especially in physics, everybody loves it when a theory doesn't work, right? Because now, what's the right?
There's something new to do.
What's the new physics there? And it kind of played into a lot of people's, you know, everybody's favorite thing, like, oh, it's a fluctuation-based theory. It's you know, something beyond the mean field. It's this, it's that. And you know, and I got lucky, basically. You know, Michael Brenner, you know, he had some sneaking suspicion that it was hydrodynamic, which the experiments should have been immune to, but it turned out they weren't. You know, the way that they were doing it, you know, they're sort of using laser tweezers and putting these colloids next to a wall, letting them go and see where they went, and then they kind of pull them back. And it turned out that by doing that, their bias, you know, the wall was also repulsive. Right? So they keep putting these particles down here, and they get pushed away from the wall by the wall, and then they put them back, right? And hydrodynamically, if you take something here and there's a wall and you push it like that, the fluid kind of has to do that to, and you know, and so you do this thousands of times, you get really good statistics. You'll actually see on average that instead of just going away, you know, and you're looking from above, right? With the microscope, you know, it just looks like they're kind of going like, oh, ever so slightly together. And so we did this very simple hydrodynamic theory, and it just got the data just quantitatively, you know, and it's sort of like there's this real like shock wave that went through the colloidal world, you know, and it was a little bit, you know, it's a little bit disappointing because you know, like, oh, if there's this new interaction, that's really great, and it's like, oh, okay, it turns out no,
it was just the fluid mechanics.
So I did that, but I had also been doing kind of doing some stuff on the theory end with using electric fields to drive flows, and so this was in the early days of microfluid. I mean, microfluidics sort of like in the kind of late 80s, you know, people started trying to make stuff in silicon chips. And in the late 90s, it started to become all the rage. Yeah, I think because, you know, sequencing the genome and all this kind of stuff. And, you know, and the idea that you could make kind of these massive multiplexed, you know, fluid computers. And so that's kind of, you know, so there was a time where there's a lot of like, let's explore different ways to make fluids flow on those scales. And, you know, and so it's this nice kind of playground for, you know, there's a lot of interesting phenomena that happen on that scale, and, you know, that you don't see at a larger scale. And, you know, and so, yeah, so I was doing stuff with electrically driven flows, electrophoresis, this kind of stuff. And then went to Caltech, and there I worked with, I kind of had this fellowship that you could do whatever you wanted. And so, you know, which is good and bad, right? I mean, it's sort of, there's, you know, you can, you know, if you're someone like me who really enjoys learning, right, and kind of like wants to interact with people, and then find some reason to do so, right, you know, that it worked really pretty well. You know, so I wanted to learn about suspensions, and so I went and spent a lot of time with John Brady, you know, who developed a theory for, so it's, you know, it's called microrheology. So rheology is, as I think you guys know, but maybe your audience doesn't, is, you know, complex fluids, how do they respond, right? How you characterize them. And so microrheology is using very small particles to measure that, you know, looking at the Brownian, the diffusive dynamics, and using that to try to understand the properties of a material. And that was sort of a new but fairly well-worn subject by the time I was at Caltech. And so what John and I did was worked at, you know, can we get the nonlinear rheological properties? You know, if you were to take a particle and actually pull it, right, you're driving the material out of equilibrium. And so, you know, could you get at things like shear thinning or a yield stress, right? So some of these nonlinear properties, you know,
right, because normally, and yeah, there's like, maybe just to give a background, you can correct me if I'm wrong, but in linear rheology, you make small movements, right? Those small movements allow you to sort of look at the response, you know, so you can relate that small perturbations to the response. But, you know, if you start to drag particles along distance, like you say, you're going to get all sorts of things that are, you know, aren't small movements anymore, right? But then the question is, you know that phenomena happens, but can you actually measure something useful, right? Like with small particles, right?
That's right. Yep. And so I did that with John. I did, you know, I worked, I spent a lot of time with Steve Quake, who was at Caltech at that time. And he was one of the big, and continues to be one of the big people in microfluidics. You know, the main thing I did with him was write this enormous review in modern physics, you know, you know, the sort of whatever 60-page review with, you know, 800 citations, and, you know, and that's a theme too. I've written a lot of review papers in my life. I kind of enjoy it. I think it goes into, you know, it's sort of a pedagogic activity, you know. You know, so and there's one thing I was going to say about that actually that's interesting, is that you know, in terms of being shaped by your advisors, and then going and doing this postdoc where I was on my own and I could decide what I wanted to do. You know, there's some ideas I had or little calculations I did where I was like, oh, that's really cool. You know, and I knew that Michael or Howard would love it, you know, or the crowd at Harvard or MIT, that, you know, like, oh, this is exactly the kind of thing that they think would be the coolest thing ever. And, you know, and then I go talk to people at Caltech that I knew. I'm like, oh, hey, let me show you this thing. And, you know, like, oh, okay, yeah. Oh, that's neat. You know, and I was just like, you know, and so there's the part of me that initially was kind of like, well, don't you get it? You know, like, you know,
this is awesome.
Back at Harvard, they would have, you know, they would love this, right?
This is not the reaction that I deserve for this. This is good stuff.
You know, but the thing that was valuable about it, so it's, you know, it's like, it's a bit like, you know, like, well, and I think it's something that most people experience when they're new faculty, right? When you're finally on your own and you don't have a postdoc advisor saying, here's your problem, do it, please, right? You know, I mean, it's a bit reductionist to say that, but, you know, like, it really made me think for myself, what do I value, right? What's, you know, not just how can I continue to impress my advisors, right? But what do I think is important, even if the person in front of me doesn't?
Right.
right? And and how do I choose problems?
Yep.
I'm sort of entering a career where I can do, I can choose my own adventure, right? I mean,
Right.
Uh-huh.
how do I do that, right? And that's
And how to think about how to justify it to yourself and to other people, right? Which is an
absolutely.
Building that enthusiasm for other people so
Right.
that they understand
Yeah,
what
that's
it
right.
is that this means.
Yeah, and sometimes you do something that, like, and you have to make these decisions all the time, but you do things that you think, this is actually really important.
Yep.
Other people might not see it yet,
Yeah.
but when we do it, they will,
Yeah.
they'll come
Yeah.
around, and and that's the, I can say this to people too, that generally, like, if you think about wanting to be a pioneer in a field, right?
Mhm.
By definition, it means that you're going somewhere that nobody has gone.
Yeah.
Right.
And it's
Right.
not, like, you can look back and it's pretty obvious that that was
Yeah.
a fruitful way to go, right? But like, you no one's going to tell you to go there because
Yep.
it's
Uh-huh.
not been done,
But
right? And
right.
so like,
And kind of by definition, people might find it odd or not understand why you'd want to do that, right?
right,
Because
absolutely.
otherwise there would be a well-worn path towards that. And
Right,
you would
right.
not be pioneering a thing. Yeah.
Right. And at the same time, it may not succeed.
Yep.
Right. So I
Yep.
mean, there's like
Yep.
all of these,
Yep. Yep.
risk assessments that you do. And so,
Yep.
really trying to, it's, how do you make progress without being paralyzed by, indecision and, like not doing something that's just too, incremental, as the
Yep.
NSF would say, right? But also doing something that's going to really be in fact impactful that,
Yep.
so it's a challenge.
And on the flip side, doing something that other people aren't doing, doesn't always mean it's a good idea either, right?
Exactly. No, that's exactly right.
So just being a contrarian for contrarian's sake does not lead
Absolutely.
to success.
That's right.
So I want to have spend a few minutes talking about this paper that you sent us, which I personally found really interesting. So this was a recent paper. I think it's just this year that it got published, if that's right.
Yeah, 2022.
July, so pretty recent. And this was in Science. So congratulations. This
Thanks.
great journal. And so I'm going to read the title. I think your title's really understandable compared to some of the titles we sometimes have of papers, but maybe that's just my background. So, but it's a two-phase model that unifies and extends the classical models of membrane transport. And this is a paper by, I assume one of your students or postdocs.
Yeah, Varun is a PhD student.
Varun, PhD student, and then with Michael Doherty and
he's my colleague. Yeah.
Great. And so why don't you explain to us a little bit about the problem that you're trying to address here, and what are the classical models of membrane transport maybe?
Yeah. So the it's a little funny, I'm a bit of an outsider in this field, right? If this isn't what I grew up doing. And so I had gotten involved with a big team of people, at UT Austin and at UC Santa Barbara, and then at Lawrence Berkeley and Advanced Light Source, sort of a big group effort towards kind of developing, kind of using the wonders of polymer science to, improve membranes, et cetera. And so, my role was going to be on the transport side, as shouldn't surprise you too much. And so as we were learning about transport, membrane transport, right? I would think about it the way that a fluid mechanic would think about it, right? Which is, okay, well, you've got this membrane, it's like a, it's some solid structure, it's got holes in it, right? And so you push a fluid through and then, bacteria comes and gets stuck and it can't go through. And so, right. And then maybe you go to like an ultrafiltration, and those are, 20 nanometer pores. And so, okay, you're not, you're filtering out a different size. And so that to me, like, oh, well, I can I can set up my geometry, I can set up my boundary conditions, I can solve my equations, fine.
Yep.
And so that's what's called the pore flow model, right? Where you actually have real honest to goodness pores in your membrane.
Yep.
And you apply a pressure gradient and a fluid pushes through, because that's what fluids do under pressure gradients.
Yep.
So then there's also what's called the solution diffusion model. And that's one, like, good ways to think about that would be in, like, if you have a gas separation membrane, think about like the tire, your car tire, right?
Yep.
Eventually, over time, the gas comes out, right?
Yep.
And your tire gets a little bit less
Yep.
inflated.
It's why my kids' helium balloons, deflate, right? And they get sad
Yep.
after a week, right? Because
Yeah.
the helium's actually going through the plastic, the polymer of the rubber, right? And
Exactly.
on the way
Yeah.
out. Yep.
But a Mylar balloon will last a long time.
Yep.
Right. And there's a lot lower permeability for that. Right. And so for cases like that, it's not like you have little holes. I mean, if you do have a hole, then it's all going to go shooting out.
Yep.
Right.
Yep.
And so in cases like that, what happens is that in that case, the gas molecules dissolve into the rubber, they dissolve into the polymer, and then they diffuse, and then they go out. Right. And so, like, if you fill your tires with pure nitrogen rather than air, they'll stay inflated for longer because oxygen has a higher solubility than nitrogen.
Yeah.
Right. And so in solution diffusion, the picture is, you've got, molecules here at a high concentration, or, high chemical potential for some reason or another, right? High pressure, whatever.
Yep.
There's some solubility, and then they diffuse through and go out. So in that case, the permeability has nothing to do with, like, the viscosity of the gas. It's the solubility times the diffusivity, right? How much gets in, and then how fast. And so for that, it's clear, right? So there's all these, membranes that do that. And so there is this class that's in between, which is like if you have a polymer gel that's swollen, right? And so you can imagine like if you take rubber and you swell it in an organic solvent, right? So now you've got, a membrane that's maybe like 80-90% solvent by volume, right? It's mostly solvent, but there's little strands of polymers all cross-linked holding it together, right? Now apply a pressure, high pressure on one side, stuff's going to go through.
Yep.
Which model do you use? Right. It's like, well, I, as a fluid mechanic, would say, well, I can kind of imagine myself a little fluid element in a continuum approximation. I could make my whole way through that membrane without ever touching the polymer.
Yeah.
Right?
So there's still flow. It's still possible to get right.
Yeah.
Yep.
Right. And so from my perspective, oh, there's a pressure, I'm being driven down this pressure gradient. I might not even know that there's polymer around, right? I'm just moving the way I'm moving. And so, okay, all right. So there's a pore flow description of that. And that's like a flow through porous medium way, but then there's also the perspective that, look, these things, they don't have actual pores. This is this osmotically fluctuating thing, right? And everything's changing all the time, right? And, it's fundamentally diffusive. The polymer is diffusing, and that's why it swells. And so what happens there is you wind up with a concentration gradient, right? There's more solvent on one side than the other, where it's being held against a support, right? And so it dissolves, there's a concentration gradient, and then it gets out, right? And so that's solution diffusion. And so basically one picture is mechanics, right? Oh, it's conservation of momentum, right? You're applying a force, and, and we know, how that works. And then the other, which is like, well, no, this is actually a mass transport problem. It's thermodynamics, right? And you're just a little bit out of equilibrium. And so, you write it in a chemical potential format, and right. And so, and so a difficulty is if you just look at the flux and you measure a flux, right? You're going to get a flux that's proportional to the pressure drop, right? For both models, right? And so the difference is the the prefactor, right? And so one of them would say, oh, there's a permeability and a tortuosity, and there's sort of like a Darcy flow type description. And the other one would say, okay, well, that's, you know, this, what's the solubility? And they'll write that in a thermodynamic standpoint. And, what the, how does the chemical potential change with the volume fraction? And so, the expressions look very, very different.
Yeah. And look like they depend on completely different sets of physics, right? Because one's conservation of momentum, the other's mass transfer.
Right.
Yeah.
But they both have to, that mass and momentum both have to be conserved. Right. I mean, it's sort of like, it's not like one's right and one's wrong.
Right.
And so in the end, right. So the solution diffusion says the flux is proportional to the concentration gradient and the pressure is constant in the membrane. The pore flow says, well, there's no concentration gradient, right? It's just, there's these holes in the thing and there's a pressure gradient. And so, right. And so, the resolution in the end was, or is, that they're both basically right, except in saying that the other one was wrong. Right. And because the thing is, what happens if you have a flow, again, like both mass and momentum are conserved, right? If you have a fluid flowing through this membrane, right? Well, as it goes through there's it's going to compress the membrane. If you think as a mechanics person, right? It's like, it's pushing, and that kind of compresses the membrane. The further down the membrane you go, the more it gets compressed, right? And if you're to look at that and measure the concentration inside there, well, you're going to get a concentration gradient, right? But you look at that from a mechanics standpoint, and you've got this fluid that's exerting a drag on the membrane as it goes through it, and that's just going to compress it in. And so the fluid mechanic would look at that and say, see, the flux is proportional to the pressure gradient, right? You could also say, well, what the thermodynamics argument would be like, oh, well, you have this concentration gradient, and that's what's driving it. And it's true. Right. That is also what's driving it. It's just the mechanics, the mechanics and the equilibrium are coupled together. So, it's a manifestation of the fluctuation dissipation theorem or the Stokes-Einstein relation, kind of however you want to look at it, that they're all interrelated. Right. And so what we did was essentially demonstrate, it was a very, very general demonstration. It was almost a philosophy paper, but where you can make the argument, basically saying, well, if you think about the thermodynamics of a membrane swelling and shrinking, right? How does that relate to the mechanical properties of the membrane, like the Young's modulus, or in this case, it's the P wave modulus, the longitudinal modulus. And and so you're able to introduce this three fluid model, which wasn't, it goes back to BO and soil compaction, right? And Tanaka kind of developed it for polymer gels. But where you don't look at the membrane as a single phase, or even like a single phase that fluid flows through, you look at it as like, okay, well, there's a polymer phase that's interpenetrated with a fluid phase. And each one exerts an equal and opposite stress on the other. And, and then so you have equations for each, and, and you do this, and it relates the properties of the solution diffusion model kind of in a very predictive and prescriptive way to the properties of the pore flow model, and it just shows that everything holds together, right? It's exactly the same thing. And I mean, maybe this is too much in the weeds, but the issue of is the pressure constant or not, like the solution diffusion model would say,
right?
That one's one where it's the two models use the word pressure to mean different things, right? The fluid mechanics use it to say, what is the hydrostatic pressure, the hydrodynamic pressure on the fluid phase itself? Whereas the membrane folks are viewing it as what's the normal stress on the element that contains both the fluid and the polymer.
Mhm.
And that for mechanical equilibrium has to be constant, because if it
Mhm.
wasn't, the thing would compress.
The thing would start moving. Yep.
Yeah.
Yep.
Yeah. And so it was this,
It's almost like interpreting between, like, there's these two groups of people and the way they think about this problem, right? And the
Mhm.
model that you have there allows you to sort of transparently see how you can go back and forth between both of those things.
That's right.
Which is
Yeah.
this really nice way of sort of summarizing it and pointing out, like, you think it's this, but it's also this, and that's a
Right.
perfectly valid way to think about it.
Yeah,
Right.
that's right.
Mhm.
And I think that, there's a series, I mean, really fascinating set of articles, where they were trying to work this out, like back in the 70s,
Uh-huh.
and, it got acrimonious at times.
Mhm.
And, and eventually there's sort of almost like a agree to disagree.
Mhm.
Right. And, and like, when I'd go to conferences, you'd hear questions being asked and people snickering, like, oh, he thinks it's pore flow. Huh? But despite that, the field has made enormous, leaps and bounds, right? So I mean, it's sort of like, so but so this is a way to, I mean, the thing that I like about it is I sort of feel like an outsider had to do this, right?
Mm.
Because I just wasn't raised in either camp necessarily. And I was really trying to figure out, like, how can, like, I don't see why either one of these approaches would be wrong.
Right.
I know
right.
how I would treat it as a fluids problem. Like, oh, I
Right.
have bead on spring polymers. I could do the,
Right. Yep.
Brownian dynamic simulation or something like that. Like, I know
Yep.
exactly how I would do that. And there's nothing wrong with that. And, and so just really trying to figure out what was going on. I don't think that normal membrane people would have bothered. But
Yeah.
the thing that's nice about it now is, now you can actually go back and forth, right? You can take,
Yep.
you can take one of these things and say, oh, actually, so say you've got a membrane, like some of the ones that we were looking at in MWET are where you've got, like a block copolymer giving like a rigid backbone, and then you'll have a, basically the membrane part kind of fills in the pores, right?
Yep.
And like, it would be really, really hard to do that as a real solution to fusion problem, because there's like mechanical boundary conditions on it.
Yeah.
Right? And so, and at the same time, it would be really hard if you're looking at a model, where, and you're doing it as a pore flow, but there's some solvent or solute that interacts in some way that changes the statistics of the pore, so, so you can really go back and forth and kind of pick the way that is most fruitful to go forward.
Yeah.
Well, it seems like this could be really important for transport and across biological membranes.
It may
because
be,
you've got solution diffusion, permeability, and then you've also got not active transport, but pore formation, and so you've got pores in membranes too that can transport by a different model.
I mean, it's entirely possible. I mean, people have used this, this two fluid model is one that's used, for a variety, for lots of gel. So on the tissue level, organ level, that kind of thing for sure, skin. When you get, the thing that's a little bit special about biological membranes is that it is a molecular bilayer.
Yeah, that's right.
And
so it's not a matrix that it has to be the same way. Yeah, gotcha.
But yeah, I mean, there's a lot of great problems in that too. So
cool. Well, I think that was great, and we're kind of running low on time, so I think we're gonna sort of push to our last question. But anyway, we'll put a link up to the paper, and I think that was awesome.
Well, thanks.
So we have a last question that we ask everybody, which is, so if you were going to go back and you had to do college again, but you couldn't do the path you took, you had to pick something different, what would you do?
There's the part of me quickly that would say, like, oh, I would do chemical engineering instead of physics, but that's that's a bit of a cheat.
It's a little bit of a cheat.
And
Sure.
so I won't do that. The thing that I think like any of the people that you and any of your students or, people who listen, it's clear that we have got just world shaking problems in front of us with regards to the climate. Right. And, I don't have the subject matter expertise. I feel like I've got technical expertise that would allow me to address some of these problems, but the whole issue of how do you pick a problem where you can actually have impact, right, is harder. And so I think if I were starting right now, I think I would go into something that would actually give me both the technical skills that you get in something like chemistry, chemical engineering, but also a way to, a way into really what are feasible solutions to the climate crisis that we're all facing. And, so that you could bring to bear the techniques and the skills and knowledge that we have with with potential solutions. So that's kind of that's what I would do. I don't know if such a degree exists, but
maybe we need to make one.
There you go.
Climate engineering. I don't know.
Well, that's interesting because I've thought a lot about how, in science, there's a little bit of playing around in the sandbox, right? Just kind of following what's interesting. And then there's this other part where it's like, well, but does that help us? Like, can we do anything with that knowledge that's created there? And so, what are the challenges that we can use the skills that we've learned to solve some of those problems? And sometimes those seem to be a little decoupled, not always. I mean, there's always a justification, but sometimes the justification for doing a research project, it comes after I've already decided this is what I'm going to do. Now I have to convince other people that it's worth doing.
Yeah, absolutely. And that's and I'm also, I can sometimes be critical of the drive, the real push for startup companies and, technologies, et cetera, out of academic labs, because, we're not actually trained in identifying markets, right? Or all of these things, right? And so one of these sort of the guiding principles I've always had is like, what I do, like ideally it'll be really interesting and really important, right? And, if it can't be both, it's either got to be really interesting or it's got to be really important, and so like as an academic, I think I'm really good at sussing out what are important intellectual questions or academic questions, things that are interesting and why they're interesting and how to ask them in an interesting way, but I would actually be more than happy to spend a ton of time on something that's intellectually not interesting at all if I knew it was really, really important, right? And the thing that you want to avoid is doing something that's actually not terribly interesting, right? But then declaring it to be important, when it's not, right? Because then you're like, then you're solving no problem. You're just deluding yourself. Right?
And it can be easy kind of by your own sort of confirmation bias and the desire to not waste time or, to justify what you're doing rather than just critically evaluate that.
And also not being paralyzed because, you don't always know, so like sometimes you just have to choose something and go and, and lots of things take unexpected turns and that's okay too.
Yeah.
That's most of my career.
Well, we really appreciate it. We appreciate you coming on today. So our guest today has been Professor Todd Squires from UCSB. Thank you for joining us. I appreciate your time. I certainly have had a lot of fun. And I think Wally and DJ have as well.
Yeah, it's been great chatting with you, Todd.
Yeah, thank you. I enjoyed it too. DJ looks like he got bored and he
Yeah, I think he had to run here for
I'm
a class or something. So
I'm sure that he actually had a
Yeah.
reason to drop off, but so anyway, thanks very much.
okay.
Yeah,
All right.
no problem.
All right.
Okay, so you've been listening to How Science Happens with Wally Paxton, DJ So, and Doug Tree. As always, please remember to subscribe to the podcast and give us a rating, as this helps others find the show. You can also find and interact more with us and our guests on Twitter at Happen Science. See you next time. Thank you for listening to this episode of How Science Happens with your hosts, Wally Paxton, DJ So, and Doug Tree. For more information about the podcast, the hosts, or our guests, please visit our website at bit.ly/howscience. For additional comments or questions, we can be reached by email at howscience@byu.edu.